All right, class, let's begin. We are in 2.4, the precise definition of a limit. And we wrote this definition down last time. And let's see, it took us a little bit to write it down. It was a long definition and for some reason, but let's go with it here. So let f be a function on some open interval that contains the number a, except possibly a itself. And we say that the limit of f of x as x approaches a is L. And so that stuff in English right there, in notation, it's right there. And we write in notation that right there. And so what does it follow? Follows this will be true if for every number epsilon greater than 0, we can find or there is a number such that, or there is a number delta that is also greater than 0, so that if delta is contained, in a sense, between a and b, then epsilon will contain fx minus L. That's essentially what that means. Now, if that just totally went over your head, that's okay. Let's take a look at a graphic real quick here, and then we'll just do some numbers just to get us familiar with this topic. Okay, so I drew a few things already here, but here's what we're looking at here. So it says this. Essentially, it's a graph here. It says this. If I pick my epsilon, so I pick my epsilon first. So look, I'm going to pick epsilon. Epsilon is going to be this large. It's going to go from here to here, right? And then we can go backwards or forward, either which way. I want you, if I pick the epsilon, I want you to find a delta. Can you find a delta? So that if we go back the other way, that delta, this little line right here, that little interval, really in a sense, right, will still contain the interval right here. So I can find deltas small enough that it will allow me to go back to the function and still contain your epsilon. Cool. Okay, that is it. That is the graphic illustration of it. Let's move on to some numbers now. So, and this is not the, let's see, this is not the homework exercises yet. This is just some numbers just to get us to understand what we're talking about. All right, so let's get us to understand just what we're talking about. And it just says prove. Prove it's true. So in this case, we're just kind of dealing with numbers only. I'm going to pick the delta. I'm going to pick the epsilon already. And then we're going to try to figure out the delta that will make that true. All right, let's go with it. So let's see. Let's do a graphic first of x plus 4. The graph of x plus 4 looks like this. My little 3 point is right here. That's 7, and that's 3. Exactly how I wanted it. And I'm going to pick my epsilon now. I'm going to pick an easy one so we can work with it here, okay? So epsilon is 1. That means I want to contain the 7 between 8 and 6. That's it. Okay, so that's true. At the end of the game, this is what I want to have. I want you to find a delta so that x plus 4 minus 7 will be less than 1. That's the game. That is the game. Okay, we also know that delta has a condition upon it. It says that x minus 3 has to be less than delta. As f of x gets closer to 7, the x gets closer to 3. That's kind of what we're looking at. Okay, what am I going to pick? So let's do it this way here. I pick the epsilon. I say epsilon has to be 1. Then you guys say, oh, that's easy, Mr. Ngiev, because delta is just going to be 0.9. I'm like, what? That is true. Yes, absolutely. That's it. We already found it. So let's prove it now. Let's bring down our condition. Condition is the absolute value of x plus 4 minus 7. And then we're going to string this out so that eventually it still has to be less than 1 by the time we get it. We're going to choose our delta somewhere during the process. Let's go with it here. So this, let's get rid of parentheses. So would you guys say the absolute value of that is the same as the absolute value of this? Okay, good. If So no, that'd be a problem. All right, would you say that is also the exact same thing as x minus 3? Okay, and here's where our delta comes in. We're saying, look, our delta is 0.9, right? So that means the difference between x and -3 has to be less than 0.9. So it has to be less than 0.9. Perfect. There it is. We substitute our delta and our 0.9 because we chose it. So hold on, is 0.9? Is 0.9 actually less than 1? Yes, yes, yes. And we're done. Epsilon was stated. We found the delta that we run this process back through. The delta is right here. We made it to be less than 1. So the most important inequality here, is this guy right here. I'll show you that in just a second here. So everybody got that. The whole concept of someone chooses an epsilon, the other person chooses a delta, so that when this process is ran through, that 1 is less than this piece here. Okay, but let's get more sophisticated, because this is going to get sophisticated. In fact, let's use the same numbers, except we're going to use a special kind of delta here, which is kind of cool. So what are we saying here is this. Since we chose delta to be a 0.9, we go back up to our list, and yes, anything that's over here is going to be less than 1. Okay, let's do the same exact example. We'll pick a different little delta here just to be correct. Let me put that all in. All right, all there. And we're going to pick whoa, what happened there? That was weird. Okay, let me do that again. I think run the slide. Let me see if that, let me just check out something here. No, it didn't do it this time. Okay, that's weird. Okay, our graph, don't need to graph it, but just to say it, there it is. There's my 3, there's my 7, and epsilon is equal to 1. That's what I'm choosing. Okay, so the absolute value of x plus 4 minus 7 will be less than 1. So you pick the delta that will make that true. And the condition on delta is the difference between x and 3 inside the absolute value has to be a certain amount. It has to be less than the delta that we're looking for. Okay, so in this case, this is the cool one. Since epsilon is 1, I'm going to say this. Delta is 1. You give me an epsilon of 1, I give you a delta of 1. No problem. In fact, is like in this case scenario, you give an epsilon 1/2, I'll give delta 1/2, and I'll win each time. So how does this work? Let's go with it here. So absolute value of x plus 4 minus 7. Let's see if this works. Again, same stuff here. X plus 4 minus 7. Everybody agreed there. And that is the exact same thing as x minus 3. So delta is 1. And remember, the difference between x and 3 has to be less than 1. True, true? So hold on. That's delta, isn't it? Right here, that's delta. And in fact, we can actually even write epsilon, right? Epsilon is this one right here. Right, 1 is equal to 1. So in fact, that's delta. This guy's epsilon. But now the question is this inequality true? Did I find the solution? Yes. Because notice, let me do this with the highlighter here. We started off here. Well, that's not a highlighter. Highlighter, okay. We started off here. We went to here. There's my inequality step. And I eventually ended up here. There's my 3 components, and we'll make that a little bit more crystal clear next time. But all of that happened because I chose a delta, which was right here. And of course, it had connection to my inequality. All right, let's do one more, and I think this will kind of clarify this little piece right here. Let me get out of. So prove that this is true. The you guys write it down. I think once you see this, at least the numbers itself could make sense. So let's go for it here. So I'm picking the epsilon again, right? Of course, I'm going to pick the easy one. So let's go with it. Epsilon is equal to 1. So you pick the delta, they'll make that true. But let's go on with this little space right here. So 2x minus 1 minus 5 has to be less than 1. All right, my condition on delta is over here. X minus 3 is less than delta. And then the question is, what delta am I going to pick? Now, here's the fun part. You guys will recognize this, especially when we do the next problem. So the delta that I want this time, I'm going to pick it now, right? I'm going to pick it because on the homework, we have to find the delta. I'm going to pick it. So I'm going to pick this. I'm going to say delta is equal to epsilon divided by 2. That's my pick. That's my pick. Let's see if it works. If that's my pick, I start off all the way back over here. I start off with the absolute value of 2x minus 1 minus 5. And would you guys agree? And again, pause the video if I'm going too fast. Would you agree that that is the same thing as 2x minus 1 minus 5? Okay, I really didn't need those parentheses in there either. Why did I put parentheses? I have no clue. Okay, but essentially you get 2x minus 6. All right, so notice real quick here. The question is, can I factor out a 2 out of this absolute value? Absolutely. Right there. Okay, if that's the case, that 2 is still going to be there. But the x minus 3, I can replace by delta. In this case, it's going to have to be less than 2 delta in the sense, right? That delta, that's what I'm picking. And those two are going to cancel off, and I got myself epsilon. There it is. Pick an epsilon of 1. We were able to choose a delta so that it makes this true. So here it is. What's the true part that we have? We started off here in the beginning. We chose a delta that made this happen. We chose a delta that we are able to put a less than symbol. And because of that delta, we came to an epsilon that fulfilled the criteria each and every single time. Okay, so hopefully that made sense. Just kind of let it sink in if need be. All right, so again, we're just looking at numbers, right? We have not proved anything yet here because we picked a specific epsilon and then we chose a specific delta, so that doesn't help. What we want to find is we actually want to find the delta that makes that true. All right, so here's what we got. Let's go where this is now is actually part of the homework questions here. So exercise 1, actually exercise 2. Not sure why we skipped 1. I don't know where it went. But let's go with it here. So we're going to start off with 2 today. Skip 1. 1 is just too small a number. We're going to prove this here. So yes, technically it's example 1, but let's just write example 2. We skipped example 1 for the day. For the whole section we skipped. Okay, so now let's actually do it the correct way. We're going to prove starting not with epsilon equals 1, but any arbitrary epsilon. We're going to get a connection that fits here. So here it is by the definition. If this is true, then this is true. And I forgot to put the absolute values right here and here. So there it is. Okay, so here it is. I'm not going to choose an epsilon anymore, right? No epsilon equals 1. We actually find we have to find the connection between delta and epsilon. Here's what we do. We take the right-hand side, which is right here, and we start simplifying. If that's true, then this is true. And if that's true, then this is true. Everybody agreed there? And if that's true, then I can factor out a 4 out of the absolute value, and this is true. And if that's true, I can divide both sides by 4, and I can make that to be true. So notice I was able to reduce this equation back down to the condition that I have with delta. That's how I get it. That's cool. So it's really taking this function, bringing it back down so that the condition of delta is met. And then I just say, oh yeah, that's easy. Delta is epsilon over 4. Da, 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 da. Now, that was just us to find the delta. Now we actually prove it. All right, that was us just to get numbers. The proof comes in right here. So we say, I'm going to prove it absolutely. You gave me an arbitrary epsilon. I can give you a arbitrary delta, or not an arbitrary delta, a condition upon delta that'll keep that epsilon exactly in its spot. So here it is, 4x minus 5 minus 7. That is the same exact thing as 4. I'm skipping a few steps here. That is true. Absolutely. And if that's true, then this has to be true. Everybody agreed there. So if there's a 4 in front of here, there should be a 4 right over here, and that's fine. So 4 and 4 still doesn't change the fact that x minus 3 and absolute value is still going to be less than delta. And if that's true, that is actually the same thing as this. And those 4's will cancel, leaving us with this. So are we done? Absolutely. Started off here. We met the condition. So eventually it is less than epsilon. For any epsilon you give me, the delta will, for this particular problem, the delta will be epsilon divided by 4, and the process will work. I'll prove it. Again, let that sort of sink in. Kind of think of it as more like mechanical as well sometimes, but it does work. Okay, next. A little bit more complicated, not by much, but let's go with it. Here it is, exercise. Looks like 2. I don't know what this is. I'm sorry, class. Can we do this here? I'm not sure why it's exercise 2 again. Can we go back to exercise 1? Please, please relabel that as exercise 1. And then this will do exercise 2. Don't know why there's a star there. Do this again, 2 o'clock in the morning. Not too cool. So let's go with it. Okay, so the only condition is we have fractions this time. We have lots of fractions this time. X over 4, 9 over 2. Whew. Let's begin. If all that is true, if 0 is less than absolute value of x minus 6, which is less than delta, then x over 4 plus 3 minus 9 over 2 would be less than epsilon each and every single time. All right. So we're set out to find our delta to make sure that's true. So on the right-hand side, let's get rid of the parenthesis here, and let's get common denominators here probably. So I need that to be 18 over 4. Let's get everything in terms of 4. That's good enough. So 3 is 12 over 4, and 9 over 2 becomes 18 over 4. Okay, and let's see. 12 minus 18 is negative 6. Okay, that's right. So I get this right here in my hands. Okay, I get to, how about this? How about I multiply both sides by 4? Am I able to multiply both sides by 4 and keep my inequality the same? Yes, that's the rules of algebra. That's the truth. That means we get x minus absolute x minus 6 is less than 4 epsilon. I think I just found my condition. There it is. Delta equals 4 epsilon. That's interesting, right? Because last time we were dividing by 4, this time we're multiplying by 4. That's okay. We just found our delta. Now we actually have to prove it finally. Let's prove it. The proof is that x over 4 plus 3 minus 9 over 2. And I'm going to skip a few steps. That okay? I go from here right to here because those are all the same anyways. And let's kind of just be a little bit more thoughtful as we do this here. So I'm going to do, that's the absolute value symbol here. That's the absolute value. I'm going to slide this 1/4 out. In fact, I'm taking out a 1/4. This will be equal to 1 over 4 x minus 6. Okay, that 1/4 stays. And we're going to have this condition right here. This guy is less than 4 times delta, or 1/4 delta. That's the condition that has to be held true. And awesome. Right there's my condition. Delta is exactly the same thing as 4 epsilon. And the 4's cancel. And have I got my true statement? Yes, I have. And again, the important pieces here are, go back to my highlighter, start where we started from, the inequality, and where we end. So the condition on epsilon initially is this. We found a delta that will prove that yes, you stay below epsilon each and every single time. So as long as epsilon is at the most really is 4 times epsilon, we still make this true. Now, could it be half of epsilon? Absolutely. Could it be 1/20th of epsilon? Absolutely. And that still would work too. But even the biggest delta here, epsilon, whatever epsilon is, we multiply that by 4. That still will keep us underneath the original epsilon. Okay. All right, exercise 3. Let's get a little bit more complicated. Let's get some square roots in here. All right, let's go with it. First things first, you guys remember that there is no such thing as a graph on the left side of this, right? So we're going to modify just a few things here. Plus, notice, look at this. We're going from the right-hand side. Ooh, that helps a lot. Check this out. Because we're going from the right side, we actually don't need the absolute values anymore because we're just going to be on the positive side of 0. So the condition changes up just a little bit here. If 0 is less than x is less than delta. Notice I don't need absolute value. I'm not going to go into the negatives. I'm not going to the left side of x. Then this is true. Absolute value. And we'll get rid of the absolute values in just a second as well. Just wanted to start off. That's the exact definition. And then it boils down to this. And since our values of 0 or x are always positive, we actually don't need the absolute value marker, so we can actually get rid of that right over here. All right, this one got to think about with numbers here. So here it is. If this is true, if I square, will that still be true? Okay, this one kind of deserves a little bit of attention here, usually. So If you have two positive numbers, I'm just going to take 4 and 8. If that's true, yes. If I were to square numbers, is the condition here still the same? Absolutely, right? Squaring positive numbers leaves the inequality alone. It does not change. I think I got what I was looking for. Let's see, I got myself delta is equal to epsilon squared. And that will for sure hold my condition. So let me write it over here. That means that of that minus that, that's my original, will be less than let's see. Are we okay with this? We're good. Oh no, sorry. Not true, not true. Let's erase this real quickly here. That's true, right here, right? That's true. Okay, and if that's true, here's the thing. That's the interesting thing is so this and this are directly correlated, right? So if that's the case, then this is true, right? Because they're directly correlated. Again, we're talking about positive numbers. So if I have a 25 is greater than 36, if I square those, does the inequality hold? Absolutely. That's what we just did there. We took the square root of each one. That's still held. And if that's true, then we got ourselves the square root of epsilon squared, which still is epsilon. So what did I prove? Given any epsilon whatsoever, I pick a delta, which keeps the epsilon true. Or, in other words, I've just proven this. That, which was my original statement, so as long as I pick a specific delta, which is this one, if we want to just put that in, as long as we just pick a specific delta, that's this, will allow us, even though there's an equal sign right here, the important part is I have an inequality right here, will allow us to still be less than epsilon any time whatsoever. Okay, are we good there? All right, precise definition of limit, geeking out on limits, that's cool. Let's see, I'm going to go to here. Okay, and then this one, we got to do this one. This one's the interesting one. We moved from linear terms, we moved to square root terms, and now we're going to move to square terms. Now, square terms are going to be a bit different. I'll just tell you that up front. They are a bit different here. So let's try it. And I'll tell you why they're different, and then we'll see how we can actually get around that difference. So let's go with it. So if that is true, it can only be true if 0 is less than x minus 3, right? Less than delta. Then we have x squared minus 9 would be less than epsilon. So try to figure out delta and make that true. We can hold all the epsilons underneath. All right, let's go with it. Let's work on this side here. So that is true. Oh, hold on. That could be factored, huh? This factored in x. Looks like x plus 3x minus 3. That is true, then that is true. And if I have absolute values, I can break them apart into two different pieces. That is also true. And here's our little problem. So notice what we have is we have x minus 3 is less than delta. We have an x minus 3 less than epsilon. That's fine and dandy. It's this piece that's the problem. Notice it's because this piece also has an x inside it, right? Remember how we factored out a 4 last time? It was just a constant. That was easy. We could just divide by 4 and everything was great. In this case, we have a, so as x changes here, x will also change here. Now we're stuck. So here's what we're going to do. The trick of the trade is this. I'm going to take, so that piece, yeah, that piece is just fine. I'm going to define this. I'm defining a value right here. I'm going to define that x plus 3, or the absolute value of x plus 3 is going to be less than c. What is c? C is any kind of constant. Just some constant, that's it. All right, so if that is true, I have this on my hands. That means that is less than epsilon. And I can divide, oh, now I can divide by c. So I got this condition, but I don't know what in the world is c anyways. So let's take a look at it. This is where the fun begins. Here's what we're going to do. Based upon that condition, we're going to say delta is the minimum. Oh, it's the minimum between 1 and something else. Right? So I'm going to do this here. I'm going to say, look, I'm going to choose between two numbers. And if this other number is bigger than 1, I'll choose 1. But if it's smaller than 1, I'll choose that. So now let's do this here. If this is 1, and I pick 1 into here, so let's do this here. I pick 1 for delta. We'll see where we're going with this in just a second here. Just it kind of doesn't make sense at first, and like, oh, okay, that's why. All right, if I pick delta is 1, that means this condition now is x minus 3 is less than 1. Okay, we're not really considering the 0 factor here because it's positive values anyways. All right, if that's true from algebra rules, we can say this. Is that true? So negative 1 is less than x minus 3 is less than 1. Right? We can switch it around over here. And do you guys remember how to solve this for x? What we did is we had to add 3 to all 3 sides this time. All right, there it is. That's what we're doing. Adding 3 sides, 3 to all 3 sides. Gets 2, less than x is less than 4. Yeah. And here's a trick that we're going to do. Notice this is x minus 3, right? We also had an x minus 3 over here, right? But as I get knowing what x is, in order for x minus 3 to stay below 1, or in between 1 and negative 1, the x value would have to be between 2 and 4. But that's not what I stop. I stop right here. Let's do this here. Let's add 3 to all 3 sides. That should be 4 plus 3. I'm not sure why 3 is missing over here. So here's what I got. If x minus 2 is less than 1, which is this little condition right here, so x minus 3 less than a 1 for epsilon this time. If that's the case, then x has to fluctuate between 2 and 4. But that means x plus 3 is going to have to fluctuate between 5 and 7. And if it fluctuates between 5 and 7, what's the biggest value that x plus 3 can ever be? Well, 5 is on the lower end, right? 7 is the higher end. So there it is. The x plus 3, the highest this x plus 3 can be is 7. Because if we put absolute values on it, there's my 7. So here's what I do. I replace that, because that's 5 is the lower end, right? 7 is the higher end. That 7 goes in for C. So there it is. It goes in for here to say that has to be true. And I have captured it. So if x minus 3 is going to be below 1, the x will be between 2 and 4. And the x plus 3 will be between 5 and 7. But the highest it could ever range up is 7. In fact, it can't even touch 7. It's going to be less than 7 always. Okay, have we proven it? Yes, we have. Let's go with it. So here's what I got. That is true, or that's our starting point. If our starting point is here, then this has to be true. And if that's true, as long as we are less than 1, right? If we, but if we're getting closer and closer to 3 for both sides, and for limits, we do want to be less than 1, right? We're going to be like super close, less than 1. Right? So if that's the case, then I'm going to say that that means that has to be a less than a 7 delta. And if that's true, if we're closer than 1, which is super, super close, I replace epsilon with delta, and I get myself still with my parameter that I needed. And done. That is it. I've proven it's this one. You need the extra little c in order to get quadratics solved. It's because you have two things that are fluctuating. The x minus 3 is fluctuating, and the x plus 3 are both fluctuating. All right, so that is the end of the rigorous proof. We're going to do some other stuff here, but I figured this would be good enough for today to stop here.